Michele Schirru is a development engineer for the Ionics Advanced Technologies and former research associate for the Leonardo Centre for Tribology at the University of Sheffield. In fact, we were communicating with him while he was at Sheffield. He has his first degree in mechanical engineering from the University of in Italy and a PhD in tribology obtained at the University of Sheffield. His research focuses on the development of novel ultrasonic sensing technologies for in situ applications in industry scenarios, ranging from engine oil analysis, that sounds interesting, to aerospace applications. For his research, he has been awarded the Institute of Physics Awards for Innovation in Tribology in 2016 and the Tribology Bronze Medal from the Institute of Mechanical Engineers. So I'm going to get rid of that.
Excuse me, what is tribology?
I'm going to ask him that. So, Michele, can you tell us just briefly what tribology is? We have people here that don't know what tribology is, including me. So while we're waiting for some more people to...
Tribology is the study of surfaces in contact. So, this includes automotive engines, so any lubricated components. But it also includes sports tribology, so for instance hockey, any contact really. So it's a very broad science really.
So basically the history of the science of friction, I guess.
Yes, tribology itself was born with a letter from Dr. Jost that showed how much money UK could have saved. Friction was the problems related to friction were improved, and so a new branch of engineering was born when they noticed that billions of pounds could have been saved by optimizing friction coefficients and so on.
Okay. We're just going to wait a few
I'll share my screen now, and when you're ready, I'll start.
Okay, we're going to wait 1 or 2 more minutes just to see if anyone else shows up. I'll give them 2 minutes, then we'll start at 5 past.
Yes, no problem.
Okie dokie. Okay, we've got you plugged in, and we can hear you not much better now because we're using the speakers of the projector. You know what? I think we can probably get started. I think maybe some people are leaving this morning and they may be checking out of the hotel. So let's get started. Over to you. And thanks very much for joining us at your late hour. Yep, go ahead.
Yes, thanks you again for the introduction and the running of the and as the introduction and background is different from the speaking modeling. I spent the rest of my career in the development of facilities network, the project with application, ranging from analysis, so basically what I was saying is that for my background, as from the introduction, is quite different from the average speaker in the room. And I actually spent most of my career developing ultrasonic measurement solution for in-situ applications such as measurement of oil, lubrication in journal bearings for low result or BP, and some other applications. However, I'm really passionate about ultrasonic in general.
Could you speak a little more slowly?
Yeah.
Go a little bit more slowly because we're having trouble understanding you.
Alright, so I'll try again. I was saying, I mainly developed ultrasonic transducers for in-situ application. Since I'm really passionate about the technology, I'm also dedicated to the application of this technology for space applications. For instance, I've recently sent over for publication a paper about a real meter for future landing missions. And my presentation today will mix my passion for exotic applications of ultrasonic technology to my field of expertise, that is measurement methodology. So, if the audio is okay, I will proceed with the core of the presentation.
Yes, please.
Yeah. So basically, for me, everything started regarding this research after reading Jim's book, Making Starships and Stargate. After a while, I contacted Jim for asking more details about the fascinating research he was conducting. At that time, I was interested in understanding better the operating principle of the device and what step had been made since the publishing of the book. After a few emails, he kindly invited me to participate in the development of the device, and of course I couldn't refuse. So as soon as I started, I noticed that there was some room of improvement regarding the device. At first, for instance, I noticed that the accelerometer that was put in line with the piezo over here could interfere with the measurement setup. And my work has since mainly focused, as I will show in the next slide, on improving this factor. Further, I noticed that the equation reported in this slide is a function of frequency and power output. Therefore, I thought that an ideal geometry could be found to optimize the value of the variation of mass. And I will discuss this briefly in the next slide. Also, I noticed that the first stacks that were made by Professor Woodward were made basically in-house. The stacking procedure was optimized over the years, and I have to say, some of the samples I saw are actually remarkable. However, this is an area where researchers and entire companies have dedicated years full-time to improve the coupling among the piezos and the overall acoustic transmission. So this kind of stacks, I'll be describing them in a few slides. And therefore, I thought that it would have been alright to give it a shot also to actual commercial stacks. So as I was mentioning previously, one thing that attracted me about the device proposed is the possibility to obtain a net acceleration, and that the mass variation is function of the power output. In literature, there are mainly two categories of ultrasonic power amplifier. They are referring this line to the linear amplification output to these devices that amplify power through geometry, to a certain geometry. And the power output of these devices can be so high that they can be employed for soldering applications. Another category that I find very interesting is the one of the so-called nonlinear amplifiers. Actually, this is a video, and I will play it. So these are non-linear because the sound propagates through Hertzian contacts, and the non-linearity of the contact modify the power output and frequency contact of the wave. In this case, on the left side, you see a compressed metal sphere chain that can be used to generate the so-called sound bullet, the one on the right. These bullets are normally used for medical applications. However, there are journal articles that shows that energy of the sound bullet is dependent on the orientation and gravity dependent. And I don't have the reference here with me, but I will be able to provide it if anybody is interested in it. So it was the practical knowledge of the existence and modus operandi of these devices that made me confident in the piezo thruster devices developed by Woodward. This consideration brings us to the core of the research proposed in this presentation. As mentioned in the first slides, we decided to give it a go with commercially available piezo stacks. So we purchased some piezo drive stack actuator. These are highly performance piezoelectric stacks that are coated with epoxy. And these are normally used in applications such as nanopositioning, microscopy, anyway, precision application, because you can control the displacement of the stack quite precisely, and in the order of the micrometer. The range of operation specified is minus 30 to 150 volts. However, the first objective was not pulsing at high power, so the actual voltage wasn't an issue. The main reason for purchasing this actuator was to have a fully characterized and certified piezo in experimental phase. And of course, this can be overcome with more exotic material once the core concepts are proven. So we purchased piezo devices, piezo stacks that are comparable with a device already prototyped in the laboratory there in America. So the results of the previous consideration, both in terms of piezo stack and resonator geometry, led to the design of the devices shown in this picture. The resonator was made of both brass and steel, in this picture is brass, to test how hardness of the material affected the overall response. The caps were made of both aluminum and plastic. Unfortunately, I didn't have the time to test the plastic one. The cap was used to dry coupling the piezo stack to the resonator, basically applying a load on the top. So samples of this device were sent to various members of GIM consortium. Let's refer to it as a consortium for the moment. The Dresden group, as far as I've understood, has used the device to actually measure thrust. And if I'm not wrong, they recently published a conference paper about this. And I didn't use them for the same measurement because I don't have the necessary equipment and the vacuum microbalance. However, I developed a methodology to measure the location of the nodes and antinodes in the device as it operates. This is important because the device needs to have the cap oscillating at the largest possible acceleration at both the harmonic and second harmonic resonance frequency in phase to produce the largest acceleration. Also, the ideal device should be mounted so as to minimize the communication of the high frequency mechanical excursions of the box in which it's mounted. All of these can be achieved with a proposed methodology. So the instrument I use to measure the stack vibration is a PSV 400 3D laser vibrometer. The principal function is the principal function in principle of the laser vibrometer. Just in case somebody do not know it, is the following. So basically, the laser generates a light beam that is split in two directions. One beam is incident to, maybe I can move this away for a moment. Yeah. One beam is redirected to a photodetector and is used as a reference, while another beam is incident to the target. Once the beam is incident to the target, it's partially reflected back, and the oscillation will, of course, scatter the light. The reflected beam is then compared again with the reference beam, and through some signal analysis, it is possible to measure the actual deflection, velocity, and acceleration of the target surface. So this slide, in this slide, we can see how the measurement is conducted. Basically, the specimen is firstly located in front of the camera on the side to be tested. Basically, the PSV 400 has both the laser but also a camera. Through this camera, the user can generate a grid of points located on the surface of the target. And these are the location at which the laser will make the measurement automatically. Each measurement is the average of 10 acquisition in this case, but it can be also higher. It will just slow down a lot the acquisition. Before the test starts, the laser finds automatically the optimum focus for each point. Therefore, it is not important to have a perfect alignment to obtain meaningful measurement and meaningful result. Once it is done, the scanning begins. And the picture on the right shows the sample of the result. At each frequency, at each operating frequency, we have a plot of the amplitude of the geometry. And for each point of the acquisition, we have a spectrum of amplitude, of displacement or velocity, such as the one on the bottom right of the picture. So this slide...
There's a question?
Oh,
What's the question?
On the
Yeah.
previous slide.
On the previous slide?
What
Yeah,
is
this
the-
one.
What is the, yeah, this, no,
This one.
next
The
one.
previous one that you showed with all the dots for the laser.
yeah.
That's the one.
Yeah, this one. What's under the resonator, that sort of metal thing?
Oh, what's holding that the
is-
horizontal?
Just a support. Basically, Jim provided us with some support for the tip, but I decided to leave the tip free of movement. So that was just an element to keep it
It's not fixed.
the resonator straight, but there's nothing to do. The resonator is free to vibrate. It's not.
It's just free to vibrate. How many points are actually on that device? So you said every single point has its own spectrum. How many points did you look at?
I can't remember the exact number. Basically, I wanted at least 10 points of the width, and since it's a mapped geometry, maybe a few thousand.
A few thousand. Wow.
But yeah, I can achieve even a better resolution. It just it will slow down the acquisition.
Hey, go ahead, continue.
Okay. In fact, you can see that this is one of the last acquisition I made, where I was interested in having a high density for the measurement. Well, in this slide, I've acquired a bit less points. So on the right, we basically have the spectrum that is obtained at a single frequency, while I acquired the data for all frequencies. So on the left, I made a GIF of the vibration of the stack throughout a series of frequencies. We can see how the nodes and antinodes are quite clear at the resonant frequencies, with vibration ranging in the order of hundreds of nanometers. So these results were compared with that element simulation completed on COMSOL. The piezo stack was simulated with PZ5H material, which is very close to the actual material used for the experiment. The cap is in aluminum and the stack was steel. The mesh was a mapped mesh with the size of 1/15 of a wavelength. This is an important parameter when running acoustic simulation, in fact. The amplitude of the displacement and the location of the nodes at the frequency of interest was very close to the measurement conducted experimentally. Now, this simulation was really straightforward, but it was clear that the finite element simulation could be used as a tool to steer the design of the resonator geometry. Especially COMSOL is indeed very useful because it allows to implement customized physics, meaning that Mach effect could be added to conventional PDE wave equations. Now I'd like to give a few considerations on the pictures on the right. It was found that most of the energy was released at the chamfer, as it can be noticed from this slide, of the resonator. And this is also measured by the simulation as shown on the picture on the left. So for some frequency, it was measured the maximum energy peak on the bottom of the chamfer and at the cap. Let me move myself on the side, yeah, so you can see better. Yeah. So for some frequencies, it was measured maximum energy at the cap and the chamfer. And if I'm not wrong, and maybe Heidi and Jim could comment on this, this is the situation at which Mach effect is stronger. However, I'm not exactly sure about this what I'm saying right now. So I'll let you comment after the presentation. Finally, I would like to add some conclusive notes. The PSV400 is an extremely expensive piece of hardware. It is very useful in the calibration phase of the testing procedure, but there are also cheaper ways to obtain similar results to what I obtained with the PSV400. One could use a single-point laser vibrometer and acquire vibrational displacement at various locations across the resonator. This was confirmed by using a CLV2534. This is a compact and portable laser vibrometer still produced by Polytech. And it was used to
explain something real quick while we're trying to find the nodes. We won't be able to publish. Michele just has this thing on the table, and sort of it's horizontal. He's trying to find the nodes along this line, so that we know where to clamp it. Because if we clamp it along this line, let's see the vibrational nodes of the acoustic. So he's trying to tell us exactly where the nodes are, so we know where to actually clamp the thing and hold it still on that speed. So that's what he's helping us with. Otherwise, we have to sort of use some pliers and hold it here, and see what the spectrum is. It's very awkward. So he's going to do that for us with this 3D analysis. Okay, thank you. I just need to explain something, but we're good to go again. Thank you.
That's right. What I was saying is that basically, instead of using this thousands and thousands of dollars piece of hardware, one could use a single-point laser vibrometer. So we tested this in a research group with a much cheaper single-point laser vibrometer. Now we could do this experiment because we had the validation from the PSV400 already in place. But what we noticed is that basically using the simple setup shown on the top of the picture, so where a piezo element is bonded on a steel specimen, we could fire a laser beam to the surface and measure the displacement. Now the amplitude of the displacement is shown on the right. And this was converted into, this experiment was repeated at various frequencies, and the results were converted into the vibrational speed of the surface along a range of frequencies. Now, notice that the maximum frequency we were able to measure accurately, the displacement was 3 megahertz. So this is quite a high frequency, considering that now the piezo stack works around up to 100 kilohertz. So for the future, if any high frequency application would be put in place, then this would be a measurement solution for it.
We can't afford a 3D laser thing, so a single laser vibrometer might be an option for us.
How much?
I don't know.
Sorry.
Oh, Michele, do you know roughly how much portable laser vibrometer costs?
I don't. Okay, I think it ranges between a few $100 to.
A few hundred dollars?
I think this one is quite cheap. I think the one from Polytech is probably $1-2 grand, but it's not expensive.
Okay. All right. Sorry. Continue again.
But I'm not sure. I will ask again to who's in charge of that instrument. But from the way it's used by the students, I guess it's not expensive.
Okay.
So in conclusion, we can say that yes, it's possible to measure piezo thruster device performance non-invasively. Node and node location can be identified with great accuracy. Commercial piezo stack should be the way forward for this stage, in my opinion, unless a customized material is chosen, and this will be probably the case when the actual application radiation resistant, temperature resistant will need to be put in place. In fact, I don't think piezo stack exists that are radiation resistant. But just on this stage, probably commercial piezo stack are very useful. And redesign should be reconsidered. However, simulation through FEM and console can help for a fast redesign in a way that is similar to additive manufacturing, where basically parametric change of devices, material, and parameters could be put in place with a programmatically, let's say. In future, I'll be happy to help with increasing the operating frequency of the device and use this methodology to detect the exact position of nodes and anti-nodes. And of course, it would be awesome to see and test an array of piezo thrusters to obtain a detectable net thrust beyond any depth. Thank you for your attention, and I'll welcome questions. Anybody has any?
Thank you.